So 2003 and 2004, that's the year this album, Deep Cuts, came out. But it's really important years for me in my life. I was in high school and taking this class that is really hard to translate in English. I'm Japanese, I went to high school in Japan, but literal translation would be something like music appreciation. And you go into classroom, you listen to Rikos, and you learn about history. But in addition to that, you watch movies with different frequency of sound and see if that affects your perception of that conversation in the movie. And most importantly, I discovered this artist called John Cage. How many of you know who John Cage is and his work? Oh, some of you. That's great. So probably his most famous one is 4 minute and 33. This is the entire score. He's a composer from USA. This is the entire score for this music. And T-act in music notation means there's no playing involved in this segment. So this entire score is just a score of silence. And however interpret this score as a performer is up to the music performers. He also does things like cartridge music, which the entire score was completely graphical and completely generative. So each participant for this play, there's multiple players, and each of them brings in this transparent sheet that has a line on it, and then they place it on the table. So not only it is visual, but also every time the score is different. And then again, how to interpret these lines into a piece of music or performance is entirely up to the performer. So this was a very interesting year for me to discover that there is a such thing as non-verbal communications. Up until then, I was interested in journalism. I was thinking of majoring journalism in college. And I realized that how you deliver stuff, not only your writing, your speaking, how you deliver stuff affects our communications. And I studied communication. Not only that, I wanted to study in the program in US, so I got to learn English first for 6 months intensely. And without that, I wouldn't be speaking this language on this stage. So it was a pretty important year for me. So now into 2016, I'm in this industry that makes a lot of nonverbal communication possible, and I make that as a web developer. On personal note, I started drawing a lot. So this is me learning last programming language by annotating the website's documents and the book that they have on the website. And to me, drawing squares like this is my representation of functional programming. And this is my interpretation of metaprogramming. And here's the static allocations. So I started experimenting this, learning something not only through text, but visually. Also, I do a lot of side projects that's related to textile making. I write code to generate textile pattern, one of which I released last year around Christmas time was ugly sweater generator or Christmas jumper generator. And when I released it, internet went kind of wild. I mean, imagine the surprise of me searching on Tumblr about my name or my app name, and this comes up. It was very surprising moment. But I love this because not only they use that, but also they use my function. So I had this button to locate that image where you want it to position it. So it's left, left, right, right. But then they use that for animation tool. Like when you're recording the GIF, they have certain cadence of animations and created this piece of animation, which was very interesting to me. But making this project involved a lot of learning about what picture is and how to communicate about picture to the computer, not only to the humans using it, but to the computer. To me, this picture is not even perfect because in this original image, I can see as a human, I can clearly see where my hairline is and where the background is. But in this computer interpreted, generated version, the line is really blurred, and I need to tell them where the line is and to make sure that the output is something interesting. So that got me really interested in learning about pixels. See, so here how it goes. So like as a human, when we see a tree, immediately without even thinking, you recognize the color, the noun associated with it, the size. A lot of information comes to our brain without even thinking. But we take digital photography and use that in our communication that's on here. And to computers, it's just like ones and zeros. And I need to tell robot in this computer to how to read this number so that they can get this orange information out of it. And I was like, this is interesting. I stumbled upon a lot of keyword about computer vision and a lot of advice about like, oh, like you shouldn't do the computer vision in JavaScript, not on the browser. You should learn OpenCV, you should write C, do the bare metal thing. And I'm like, okay. But then I remember the John case, and I was actually looking at his interview recently, and he said, when I hear music, it seems to me someone is talking about his feelings and relationships. And I was like, yes. When I'm dealing with pixels, when I was making this up, I felt like each individual pixels are tiny humans, and there's like a social life to it. So I would like to think the computer vision as just understanding the world of pixels and making sense of it. So today, with 25 minutes, we want to go into how to make sense of this pixel world. In order to transport it into this world, you need a little bit of a code. And I use Canvas. So HTML5 Canvas is an element, the HTML element, that let you draw pictures in JavaScript. So perfect for this job. You create a Canvas element and give the height and width. But by itself doesn't do much. I like to think of it as kind of like buying a piece of land, but you don't really know where the neighborhood is or like what kind of language that they speak. You need to create something really important called a context. And in my demo, I'm using 2D context, but you can give WebGL to do the GPU programming. Once you create a context give you a set of language to talk to this canvas. Things like draw image. So you get another image element and use the draw image method to put the image inside of the the canvas, and then get image data to get data out of it. And this data is ones and zeros that I was showing the computer is watching. So what does that data look like? Just imagine that you have a tiny 3x3 pixel, super enlarged into a screen. And on the left, the text is what the image data, the actual object that comes back from the method. So some of them are pretty straightforward. Width and height is width and height of the pixel. But then there's a thing called data that is a flat array of numbers. And what is this? I didn't even know how to read this stuff. Turns out you need to understand what pixel is, and you just kind of picked it. So under each pixels, at least on the computer screen, there's 4 numbers, 3 of which you can think of it as a light bulbs. Light bulbs illuminating on different levels, and each of them are red, green, and blue. So how bright each of the color light bulbs changes the color of the pixel. So if I all the way up the blue and then turn down the red and green, then it gets blue pixels. And interesting thing is when you have a same number for 3 light bulbs, then you always get gray, no matter what. Okay, there you go. And then the last part that I was just touching is the opacity value. So if you light a CSS RGBA, then should be familiar that it is just when 2 colors are overlaid in your software, telling computer how much of the color to blend it in. So 4 numbers for each pixel. That means you can look at image data like this. Each of 4 start with top left corner, going down to the bottom right corner. So you can think the one set of 4 as a 1 pixel. So if I change this number, say the first one is red light bulb, so turn off the red, and then turn on the green, and turn on the blue all the way up, and then opacity is 4 on right now, then you change the color of the pixel. And this is the very basics of how you're going to do image processing. And we're going to talk about what kind of method that we can use to change and get interesting effect. So now that we know how to get to the data and kind of like put it into the world of pixels, let's think about social construct, right? Everybody has a social construct. We live in a world. I think of it as like image filter, as introducing social construct to a world of pixels. So the original filter, you have input of, let's say, red value comes in at 127, output would be 127. If green value is 156, output is 156. This rainbow scale just indicates that all of the RGB colors go through same filters. And because I am inputting the data and outputting the same data, you get the same pictures. However, you can change these filters to change the brightness, so all of them get slightly brighter or darker, or change the contrast of an image. So in low contrast situation, you can see that input is fallen from 0 to 255, but the output is right now limited to 79 to 176, so the color is limited on the output. And it doesn't have to be straight line, it can be curved line or it can be steps. And I really like this effect of filter posterize to limit the amount of color that's in the picture. And you can kind of get this like pop art effect going on. So we talked about how to change every single pixel's color based on input and output and passing through the filter. But how about changing the structure of image, like blurring a photo or sharpening a photo, like you do on the Instagram? I like to think of it as like thinking about the pixel social graph and applying that to this community. In image processing term, it's called convolution filter. So you have this target pixel that you want to change about. So let's say you want to blur. Pixel is always surrounded by friend of pixels. And let's think for the moment, when you want to blur, you want to blend it into your friends. So you rate yourself and your friends equally. You get the average color out of all of your friends' circle, and then that becomes this pixel's new color. You do that for every single one of them. So in this picture, I have very distinct pink line going through, and do that for every single one of them. And you get a blurred image out. So this is box blur, one for everything, so basically blended in flat, and this is original, this is blur. But then, in reality, your friends are not all equal. You have your best friend and you have your distant friend. So you can use something like Gaussian blur, which use normal distribution to give higher points to your neighbors on the four sides, but then lower number to the corners that is slightly distant. And if you ever wonder on putting a blur filter on SVG, you have to type Gaussian blur. That means that they're using this convolution matrix. So sharp is completely opposite of blur. You want to stand out. You don't want to blend it into your friend's circle. If the friend does something, then you want to run away from it so that you stand out more. So you lay yourself really high, and then your friends really low, even -1, and then you get sharp effect. So those are the few filters. If you are interested in these, I have a library that I created this year called Graphy.js, which I tried to make it kind of like underscore for image processing. So you can just pass the image data object and change the filters and levels to kind of prototype what you want to achieve for your image project. So check that out. So we've been talking about changing the colors and making it fun or pop or something. But then what about identifying what's inside of the picture? If I take a picture of a tree, can I make computer to say that's a tree? So in order to do that, we need to do some kind of segmenting or labeling. And same as we think of a society, like, you live in certain neighborhood and you are labeled to, certain things like hipster or certain things like upper class. And, you generally have your location associated with your label. So just do that for pixels. In order to do this, there are 3 steps that you need to go through. The first is grayscaling the image. Because it is talking about what's inside of you don't really care about the color information, so we are going to make it grayscale. Again, each color has 3 numbers. Grayscale means all of the 3 have the same numbers. So let's just do like average of all 3, and this is the grayscale that I got. Looks pretty good, but there is one problem. In color image, this green square looks a lot brighter than the blue one that's here. But then in the grayscaled version, because it's all 2 zeros and 255, it gets the same number. And this is the bias in our eyes, the human eyes. The human eyes see green more, prefer green more. So when you have more green coming in, then it feels like it's brighter, even though on the computer level, it's the completely same brightness. So you can use some adjustment formula, like Luma coding that I'm using, basically just giving green advantage and then blue and red not so much, and get more natural, quote unquote, to our eyes looking grayscales. So once you have a grayscale, let's say you want to isolate this Thunderbolt icon part, and because that's the point of interest, you need to pass through another filter called threshold. And in this case, it's completely turned on or off. So any pixel that's coming above 127 gets white, and then anything below that gets black. So you can adjust this threshold to isolate the point of interest. And then if I were building an app, I would have set a threshold to here 1670 and move on to the next step. So next step is really interesting. So we have a color image. Again, imagine that we have a tiny image, for example, and then enlarge it into the picture. And let's say your point of interest is these 2 pale pink part. You grayscale it, and then you threshold it so that the pale pink part gets white and everything else gets black. And again, as I mentioned, all of them are pixels. And a computer, 2 computers at this point, computer only know that how many black pixels are in this picture and how many white pixels are in this picture, and they don't know anything other than that. So we need to tell them how many blob of white pixels in this picture. So we need to do something called labeling. So computer go through each pixel from top left corner to bottom right corner, finds white pixel. And okay, this was the first one, so I'm gonna label it 1. And then go through again, second row, find another pixel. Is it connected to the label that I already know? Answer is no, so it labels it 2. And another one, this is interesting. So human eyes, it is obvious that it is connected to one group, but computer at this point don't know any of that spatial information. So it simply asks the question, is this pixel connected to the pixel that I already identified? Answer is no, so you put 3. The next one, this time clearly this pixel is connected to 1 and 3. So computer says, okay, I'm going to make it into group 1, but also take note that group 3 was also connected. And then do that for each of them. And then go back to the group that you memoed and ask again, saying, are these pixels connected to other group? Indeed, it is connected to 1. So turn those to the 1 group. And then voila, you have 2 group identified in this image. So at this point, computer can tell how many interesting objects are in this image, and then how big the size of the object is. However, things that they don't know yet, computer don't know yet, is this white pixel at the edge of that interesting part, or is this pixel inside of that interesting region? They don't know the border of the pixel. So we do go through the pixel again to define the border. Again, go into the first white pixel you find. Because it is a first one, it is a border. And then this time, work through a different ways. Ask your left, say, is this white? No, it's black. And then go down. Is this white? Yes, it's white. Then label that as a border. And then do the same thing. Is this white on the left? No. Corner? No. And then bottom, aha, find a white pixel. So borders that. And then go through, and computer finally knows the border, where the border is. And that means the computer knows what the length of circumference is. So believe it or not, with these 3 steps for labeling, you can do something interesting like fingertip detection. What if I want to do hand gesture app and detect when users are holding a hand? How do we go about that? So imagine that we are taking input from the photo, and you have a hand, and you already grayscaled it and threshold it so that the hand is the only part that you have in the picture. And you already go through the edge of the picture. So every 10 pixel, 50 pixel, depending on the size of the object, but consistently you put a points of interest in it. And then on each 3 points, you find the angle between those 3 points. And you will notice that on the fingertip, the angle will be smaller. But then on the side of your hand or the crease of the finger, the angle will be much wider, closer to almost going full circle. So then you can say, okay, this is a potential fingertip location because the angle is very small. Also, you can do very simple math. Because we already know size of the image and edge of the image, you can find the center of mass of this image. And then you draw a line between those 2 points. And ask yourself, saying, so I have this length from center of gravity, the mass, to the point that might be fingertip, and then point that might be crease. Does this proportionally looks like a hand? And this is something that you have to experiment with users, and you have to find your kind of threshold. But then if it does, then voila, you find a finger on your hand. So once you have those small information, things that you feel like it is a magic and it is something that you have to write a C program for, or somebody who studies computer science have to write it, it's just the small steps, but you have to define those small steps to get to the information you need. There is a very convenient functions already figured out by people. So let's say you have 3 objects, and circle, square, and triangle, and ask this picture, can I find a circle in this image? There's a handy math function already made called circularity shape factor. The formula is down there, but we already know this numbers. Area is how many white pixel in this one label, and circumference is how many pixel did I count it when I going through the edge of this object. And this factor returns 1 if the object is really circle, the real circle. And then as the object comes further away from the circle, the number goes down. So I use this function to create this a little demo. So I run a meetup in Brooklyn, New York called Brooklyn.js, and for our 2nd year anniversary, we created this socks as a swag. So you can see how the color image gets grayscaled, and I'm thresholding it, and I'm hoping that lighting works. So let's test it, that if this is a JavaScript socks or not. And then it's like a JavaScript socks, right? But then I bought this, oh, thank you. Yeah. And then I bought this triangular socks from Happy Socks. I think it's a Swedish company. And let's see if the light thing works. I threshold it too so that it's, it might be difficult to find it. Let's see if I can find this. This maybe works. This a little bit looks like a triangular, so let's test it, and it says your socks is not JavaScript powered. So this is using the same function where I detect the one object and then ask computers, is it circle or triangular? And it just says, it looks like circle or it looks like triangular. So let's see. When you are making application, That's all to it. Like you now know all of the information to create amazing computer vision image processing application. But one thing, if you are making web application, you should be careful of. As you saw, if you're doing the convolutions or the social graph, there's so many pixels and so many calculations to go through. And JavaScript is single-threaded, and if you run it on the browser, you quickly get sat Chrome or sat Firefox. So I made this app that creates a fake tilt shift image. So I kind of select the point of interest, and then I start processing image and put a blur filter again, very calculation heavy filter again and again to create kind of like a fake depth of field. And hopefully you can see on the screen that it's kind of slightly blurring and the further side is more blurred than the one closer to the region that I selected. Anyway, so that's the app. I was making it completely in the browser, not using any off-the-thread method or WebGL or anything, and I killed it. I was testing with 400 by 300, which was great, and then I released it, and people uploading like 2,000 by 1,000, and I'm like, died. So I was like, I need to figure something out. Turns out the browser has something really convenient called Web Worker that let you run your calculation off of your browser UI thread. And when I heard Web Worker thread off of the browser, I mean the UI thread, I was like, but JavaScript is single threaded, and what do you mean by off the thread? And like, I make websites, I don't make OS, I don't really understand. But to me, understanding visually again came to me really easy to understand when I treated Web Worker as an international space station. So this is something you launch from the OS that you control, which is the browser. And you have a full control, that's your object that you launched, and you can communicate data over it. And then you do all of the scientific research or heavy calculation in the International Space Station, and then get the data back to the Earth or the dome land. However, because it is outside of the dome planet, you cannot access the UI from Web Worker. So there's no window object, there's no click event for the UI buttons. You can only communicate in data. And you might be asking, because it's 2016, how about Service Worker? Service Worker is like that, but it's like UFO. Like, there is certain, the Web Worker is something that you control the life cycle by your application, but then Service Worker comes with more of the browser magic that browser takes care of it, even though when you're not looking. So this is a little more unknown territory of how it's handled, but both of them, same idea off from the browser land. So using Web Worker is super simple. You create a new worker and pass the JavaScript that you want to learn on the worker thread, and think of that as launching an International Space Station. And then inside of the Web Worker, as I told you, there is no window object access. So even though you might have your underscore handy method in your application on the browser side or UI side, you have to re-import it inside of the worker.js. You use import script. But once that's ready, then between two, you communicate by post message method and on message event, and you pass data. So while you deal with computationally heavy, expensive operation on the worker side, you can deal with your UI element on the UI side. And once you don't need it, you can just send it to black hole by calling terminate. But the point is you control the life cycle of this worker, unlike Service Worker, where once you start it, it's running in the browser. So in the demo app case, this is the app that I did it in the UI thread, and immediately after I started processing, the UI stops. I put the animation for the guide, but it's just completely junked up. And then once the processing image is over, then it comes back with all the click events that was accumulated. Yeah, there you go. Accumulated inside while I was processing this image. And it runs slower too. But then I workerified this app to do the heavy blur calculation on the Web Worker side. And now once I start processing image, animation walks through, UI element still works. And you can see that gradually the blur is getting added. And it's just as much more good user experience to the users. JavaScript running on the browser is not going to be as fast as your C program that you run on your computer locally, but you can trick it by using methods that's available to you in the browser. And I think as web developers knows how to use that to our advantage, and I really encourage you to use that. So hopefully, with this 25 minutes or so of talking about pixels in social sense, now when you see digital image, you see googly eyes, I hope. If you are inspired by this or interested in going more, I have two recommendations to go. One is Book of Shaders. This is also the tutorial run by artist Patricio, who created a tutorial for WebGL GSL shaders. So if you want to do these computation on the graphics card, definitely check that out. And then the other one is machine learning for artists. Jin teaches machine learning class at art school in New York, and he screen recorded entire semester worth of material and put it online. So my method was to define step by step what these objects are, but the other method is to give computers massive amount of reference and then asking them, does this look like the one you already saw? And that's machine learning. And if you were interested in that path, check that out. It's quite interesting. Every time I talk to people about these pixels, people ask me like, I'll back your Kickstarter if you write a picture book about pixels. So I have a page that's set up that I don't know if people like it or not, but you can, if you like this talk, you can go to my website and just click on the button and it will send a direct message to my personal Slack saying, write a book. So you can ping me that way. So again, that's my Twitter handle. If you have any questions, concerns, comments, feel free to DM me or mention me. There's a 2 project that I mentioned. Thank you very much.